Hello.
Well, so today we start developing a basic concept of signal space. We are now more or less ready with our understanding of Gram-Schmidt orthogonalization procedure, and we know that to design a set of m signals, energy signals, each limited over a time duration t, capital T, we need some n number of basis functions where n is less than equal to capital M following Gram-Schmidt procedure. So, today I am trying to look at it in a somewhat different manner, adding some more concepts. So, I am saying that for a conveniently chosen set of basis functions phi j t's, okay, we know that the m signals, m number of energy signals can be expressed in this manner. Okay. And there these coefficients Sij's, these are just constant coefficients, okay, they can be found out from the signals and the basis functions following this relation. This also is known to us. Okay. Then can I say that each signal SIT, okay, has got n such coefficients, and I can, instead of talking about signal, okay, I can also visualize it as a signal vector SI bar, where SI bar consists of these coefficients, okay, SI1, SI2, SIN. So, once I have chosen my set of basis functions, and if I once I know, if I tell you this vector for a signal, you should be able to reconstruct SI t, is it not? So, from the signal, instead of again describing calling it a signal, I can have a more mathematical description and can say that, well, a signal SIT can be equivalently represented by a signal vector SI bar, which is nothing but this column matrix, okay, which has got n capital number of n elements, because all these coefficients are related to n basis functions through this, and hence SI bar is this column matrix. Okay. And if a signal now is being viewed as a vector, what can I conclude? Can I show a signal, represent a signal pictorially instead of drawing its variation with time? I am not calling it a signal so far. So, I won't like to draw it against time anymore really. I am trying to go for an alternative description. What is that? I want to picturize this signal vector. That is right. Yes. So, we have to visualize an n dimensional space. Okay. That space is known as the signal space, because our intention is to represent signals there. Okay. So, we try to show these m signals or vectors equivalently in an n dimensional Euclidean space. Why Euclidean? Because the dimensions, okay, are orthogonal to each other, is it not? Okay. I have got, here is one diagram really, where it should be somewhat self explanatory. You just look at this diagram. This is a simplified two dimensional space. Okay. One may say two dimensional signal space. The two axes are defined by the basis functions phi 1 and phi 2. Okay. It is redundant to write it as phi 1 as a function of t. It is not necessary really. Okay. So, I can even, you can even consider a unit vector along this phi 1. Okay. Phi 1 t again can be viewed as a vector. Yeah, isn't it? So phi 1 indicates and phi 2 indicates the corresponding dimensions or axis simply. So, this is an example of a two dimensional signal space, and in general one can have an n dimensional signal space. Okay. And as is obvious here, these two axes are perpendicular to each other. Okay. Now, once we have been able to define a signal space, we can go for different kinds of measurements, and from time to time we can relate them to the basic features of the signal. We are not going to forget the signal feature of the of SITs really. So, what we can say is that each of these m signals can be represented by a point in this signal space. So, there will be m signal points, okay, in this signal space, and the line joining this origin and that point is the signal corresponding signal vector, like S1 is this vector, okay, S2 is this vector, S3 is this vector. Okay. And because it is a two dimensional space, we know S11 is this length, S12 is this length. Is that okay? Similarly for S2 and S3. So, it is easy now, because once I can visualize the point, I can also guess the corresponding coefficients S11, S12, S13 or S21, S22, like that. Okay. Now, should there be some concept of the length of this vector? Amplitude of the signal. Now, my question is, should there be some should this concept be somewhat useful, the length of the vector? Yes. Yes, why not? Isn't it? Okay. And his guess or quick guess is that it is related to the amplitude. A better statement? It is related to the energy basically. We will see shortly that it is nothing but the square root of the energy of the corresponding signal. So, what about argument? Pardon? So, he is asking about argument. Okay. So, which angle, say for S1 vector, the angle subtended with this phi 1 axis, is it going to be useful?
So, for defining S11 that is used, for finding S11 it should be S1 into cos of that thing. So, S11 and S12
Right,
finding that argument would be
right. So, why not again see any parameter like this length of this vector, angle, etc., everything should be useful in some context or the other. Okay. But my only point here is that okay, this is a simplified two dimensional signal space. Now, think about an n dimensional signal space, okay, and then define a better angle if you want to really make use of that angle property. Yes, so it can be measured. Yeah.
Didn't we say that S11 and S12 should be orthonormal? So in that case, shouldn't their amplitude be?
See, S11 and S12 they are scalars. Is it not? They are constant coefficients. Hmm? So, the length of the vector, okay, projection of the vector along this phi 1 axis. That is it. Okay. Now, the length of a vector is called as norm, okay, and this is one common symbol used for that. Okay. SI bar, norm of SI bar, and this square of this norm one can find out by simple calculation, which is nothing but the dot product of vector SI with itself. Okay. That dot product I am just representing by this notation. So, there are various notations. So, I am within first bracket I am putting the two vectors SI comma Sj, but here specifically it is the dot product of the same vector really. So, it is SI comma SI is the inner product, and this ultimately leads to this simplified expression that square of the norm of the vector is summation of Sij square, j varying from 1 to n. Okay. And this parameter incidentally, summation of Sij square is nothing but the energy of the signal. Energy of the signal SIT, let me represent it by EI. Okay. In general, it is not necessary that all the signals, all that energy signals will have the same energy. You have the freedom really. So, the energy expression in general is integration of Si square t dt over 0 to t, okay, that again can be shown to be equal to this summation of Sij square j equal to 1 to n, which is nothing but the squared norm of the corresponding signal vector Si. Okay. Similarly, I mean partially answering his question of angle, the cosine of the angle between any two vector Si and Sij or Sik is this expression. is the inner product of Si and Sij, these two vectors, divided by the norm of these two vectors Si and Sj. In some cases you may find for some demodulation strategy you may fall back on this angle between two vectors. Okay. Again there are various modulation techniques where the amplitude may be sufficient or the magnitude of the vector may be sufficient. Okay. But there may still be some cases where there are really where both the angle as well as the magnitude may be of interest to you. Okay. And then the square norm of the difference vector between Si and Sk. Okay. The square of the norm of the difference vector between Si and Sk whenever necessary is nothing but this expression can be expressed in this manner. Okay. These are just simple identities I would like you to verify for yourself, okay, to save time. I hope you will be able to do that. If there is any problem you can let me know later on. Okay. So, by these simple things if I just look back to that two dimensional signal space, okay, we can see that with these basic expressions we have been able to represent the m signals as m vectors or m points in the signal space, okay, and the actual vector is that line joining the origin and that point, okay, and the length of each vector is nothing but the square root of its energy. Okay. But this if I consider a difference vector between S1 and S11 and S12, okay, then that is not the energy of the difference vector. Please see that, you can verify from that expression. But anyway, this is the length is the square root of the energy of a particular vector, and this vector has got n dimensions. For a two dimensional one, these are the two lengths, two coefficients S11, S12. Whenever we are interested to find the angle between two vectors, we can also find that by following that expression. Okay. Now, one just comment at this moment is that we will see later that this two dimensional signal space happens to be a very important one. There are several modulation schemes which are defined over this two dimensional signal space. Okay. So, if whenever it comes to description of specific modulation schemes, you can also say that okay, this modulation scheme is a two dimensional modulation scheme, this modulation scheme is a four dimensional modulation scheme. You can also talk about the dimension of a modulation scheme. Okay. Now, sorry, the next question I am posing to you is that can you guess how we can make use of this kind of signal space for our purpose of understanding a basic detection procedure. See, this diagram is useful for understanding what the modulation process is, because we said at least qualitatively that falling back on our general description, block diagrammatic description, that is sequence of information bits, okay, can be viewed as sequence of information symbols, where I can define a symbol more generally either consisting of one bit or a group of bits. So, I will have finite number of symbols. Now, let me say there are m number of symbols. So, we need to design m signals for m number of symbols. Okay. And of late we are discussing about how these m signals can be designed. We now know that m signals, design of m signals should be based on n number of basis functions. Okay. Today we are talking about showing these m symbols in terms of a signal space where these basis functions they are defining the corresponding dimensions of the signal space. Okay. Now, is it not that after we transmit these signals, okay, that means after we transmit these symbols I can say now, okay, through some channel, we have to address the question of how I am going to detect or how I am going to decide ultimately which symbol was transmitted. That is the fundamental problem of transmission and reception, is it not? So, we are inching towards that. Okay. So, I can say that if you tell me after understanding this signal space, if you just draw, say again for an example, a 2-dimensional signal space phi 1 phi 2 and show me the location of m points, perhaps I understand your modulation scheme, is it not? Because the moment you look at m points, I know the energy carried by each symbol, okay, each signal, okay, where one signal corresponds to one symbol, information symbol, and then I also know how they are separated, what is their, what are their relative locations. So whenever necessary I can find the angle between them, and that's how I can say that I know your modulation scheme. Am I wrong? No, isn't it? So I can describe a modulation scheme alternatively by such a signal space description. Let me try. Let me just try okay, once. Yeah.
Represent the modulated signals or signals modulated symbol or symbol before modulation.
What is his question understood? His question is that in this signal space, do I represent the modulated signal or the signal to be modulated? I say he is incomplete. He should say, instead of only modulated, he should say carrier modulated. If he is going to say carrier modulated signal or the signal which is to be modulated using a carrier, that means the baseband signal. Okay, I am deliberately not answering that. Somebody else should tell me why. That is not necessary at the moment. That's not necessary at the moment because
modulation scheme
yes,
doesn't represent any signal. It represents actually a modulation scheme.
yeah.
So the point neither representing that or this
See,
one modulated signal or modulation scheme.
it's a generalized description. Yeah, his explanation is good. Yeah, the point is that all this discussion is valid for a narrow band transmission scheme, which means that after carrier modulation, the signal that I will get will have narrow band, and hence I shall be able to equivalently represent it by its corresponding low pass representation, isn't it? And this low pass signal we know is a baseband signal. Now, if I tell you that okay, these are my low pass equivalent signals, okay, and this is my carrier frequency, I tell you the same thing. Okay, when I say that this is my carrier modulated waveform, these are equivalent descriptions, is it not? So if I give you a signal space description in terms of a baseband signal, okay, and tell you that okay, my sinusoid are my modulating carriers are sinusoids, a sine and a cosine, which are already in phase quadrature, which are already orthogonal to each other really. I tell you the same description. So the question is not very important. At least we won't like to sacrifice our generality in the description, okay, by saying that okay, no, this scheme is valid for modulated scheme, this scheme is valid for non-modulated only baseband signal. No, so far this is valid for both a baseband signal modulation scheme or representation scheme as well as a carrier modulation scheme. We'll see that. Okay, that means either you talk about a carrier modulated signal over a duration 0 to t or a corresponding baseband signal over the same symbol interval 0 to t, okay, both can be shown by the signal space description. Is it okay? Okay. Now suppose yeah.
So you said that looking at the signal space, you will be able to say what modulation scheme we will use.
The scheme, yeah, but I'm not going to, I won't be able to tell you the exact signal shape against time. I may not be, because I have never said, that this signal vector S1 represents only a special kind of signal waveform. A very simple example is whether if this is my time duration 0 to t, whether the signal is like this or like this, I cannot say. If both of them have the same energy, okay, then both of them may map onto the same point in the signal space. So yeah, yeah. So I'm not talking about frequency analysis at the moment. I'm talking about, see, I'm talking about how I'm trying to describe the modulation scheme okay, not exactly completely, okay, but that exact description will be given, okay, with certain additional inputs over there. My intention here is to describe the overall scheme so that we understand the philosophy for detecting and receiving the signal back in a nice form, and in the process also how to define the signal, what are the general properties which must be maintained amongst the signals which I am thinking of transmitting. But as I said at the beginning, really I am not addressing the more specific issue of how much bandwidth is going to be necessary exactly, okay, fine. So this description is not all, this have to be supplemented with more specific descriptions. So when it comes to bandwidth description, we will address whether it is good to transmit this kind of pulse or this kind of pulse, okay. So but the overall scheme remains the same, scheme for modulation, scheme for demodulation, the strategy or principle for demodulation, okay, that will remain the same irrespective of whether you transmit this pulse or this pulse, okay. So now suppose I mean just to give you a quick example of how much we can understand about the modulation scheme and if anything beyond, let me say that I have two signals to transmit, very simple scheme, okay, exactly corresponding to the binary sequence, where I am visualizing that one bit is equivalent to one symbol, and because there are two symbols now, two bits 0 and 1, so I need two symbols, and hence I need two signals S1t and S2t to be defined, okay. And now I am falling back on my signal space description, and let me say that one point is here, okay, I am calling this as S1 vector, okay, this corresponds to S1t, one symbol, which may correspond to your logic 1, which may be looking like this or anything else, okay. Yeah, see phi 1 and phi 2, they are orthonormal to each other. When we define them, okay, these shapes are decided, okay, in this baseband form, yes. So we are not yet defining, because let that be really. So once I specifically choose phi 1 t and phi 2 t, these shapes will be decided, yes, true, okay.
No, but that will also depend on the vector S11 and S12. The final shape which we are going to get.
Louder please. Now his question is, definition of phi 1 and phi 2 will be dependent on S1 S2.
No, sir, then the final shape will depend on
Let's get back. I mean, this discussion is important really. See, in our Gram-Schmidt orthogonalization procedure, how did we start? We started with SITs, then brought in some concept of phi j's. In the process, they are related through some SIJs, isn't it? How are they related? They are related in a sense that if I know two of them, I know the third one uniquely, is it not? Okay. If I know only one of them, or if I decide for some other reason like bandwidth, like etc., if I decide about one of them, then again I have a freedom between the other two, okay. My description at the moment is that let this description be as general as possible, but when you are actually designing some system, you would like to decide about these one by one as fast as possible, isn't it? So we are not talking about a specific design at the moment, okay. I am trying to understand the general utility of this kind of signal space and what kind of general information I can get. So towards that, I am not really looking for a specific example for SITs, like when I said that let there be two vectors S1 and S2. So they should correspond to two signals S1t and S2t. S1t or S2t, there are multiple options. You have to choose one, the one that suits you most for your application. I am not going to address that at the moment. That's not necessary. My simple point is that that's not necessary at the moment really. Okay, but yes, once, because I know they are related really, okay. So maybe that if I have already decided about phi 1t, see for my discussion it is not, I am not going to ask you what exactly phi 1t is looking like, I am not going to ask you. But if you decide Well, then of course, after you have chosen phi 1 t and phi 2 t, okay, and if you decide about these coefficients, you have effectively decided S 1 t and S 2 t set. Do that, okay. But for my general discussion, that is not necessary at the moment. What is necessary is that these basis functions have to be orthonormal to each other, okay, and hence, so let me continue with my general description, okay. So I have considered two orthonormal basis functions. So this is a two-dimensional signal space, and what I am assuming is that let there be two signals. So these two signals means there are two signal points. There should be two signal points in the signal space, and each signal point will ultimately correspond to some signal set. Okay. Now, if this is one signal vector point, okay, the corresponding vector is this much, this one. Okay. In fact, if you follow my discussion, these are open issues really. We will address this specific issue later on, that where should the second signal point be placed? Let me ask you somewhat prematurely.
So parallel to it.
Okay, one at a time. As far as possible. That's a good guess. As far as possible.
So on an axis perpendicular to it.
S2 where was my question. So one suggestion is as far as possible from S1. Okay. Yes.
So on an axis
Some
perpendicular to
parallel.
it. Yes, so perpendicular to it.
Perpendicular to vector point. What is perpendicular?
So the vector is fine, sir.
Okay. So any vector which is perpendicular to this. So you are not suggesting anything uniquely. So maybe if this is the vector, so the other vector may be like this, and the one that goes to the origin.
Probably that one, sir.
Okay. So maybe any point on this line which is perpendicular to this.
Which has the same energy value.
Okay, good. So perpendicular vector, any point. A good hindsight has come is that same energy. Okay. Any other suggestion? There was one more suggestion here. Is that all? Is that all? Let me remind you a little bit. Why did you become cautious about these issues? Ah, yeah, that's the point. He is worried about distinguishing these 2 points somewhere at the demodulator or receiver. Okay, distinguishing from what? From these two, because there will be problems of noise, interference, etc. Isn't it? So there is some kind of sense of measure of separation between 2 points, between the 2 points. S1, once it is placed here, S2 must be so separated, maximally separated perhaps, isn't it? That's what was the intention. I could see somebody said as far as possible. That was a good uh, suggestion, quick suggestion, but has been countered to some extent by the third point of same energy really. See, as far as possible, let me just tell you is that might be anywhere. The signal space is not limited, mind you. That means a signal can carry any amount of energy if you have that much really, if you can afford that. Well, so now is a much better, and in fact the accurate one has come out rather intuitively, is that it should be opposite. Opposite in which sense? Yeah.
We have only two signals, then we can have only one basis function. We don't need two basis functions.
That's another point. That's another point. But I was going to extend this. I was going to extend that basically after one intermediate point really. In fact, let me tell you, even when we'll have this example, in fact we are studying that, isn't it? What is that modulation scheme? Yeah, BPSK is an example where you transmit two signals, S1T and S2T. Okay, you should think about the corresponding baseband signal set. Fine, +1 -1 perhaps. In fact, one is the inverted version of that, where the scalar coefficient is -1. So you need one basis function actually, phi 1, to define the modulation scheme. Still, it is good. Okay, I'm not telling you to define BPSK in terms of two quadrature carrier, because the same description of signal space will be used very extensively for finding out the operation of the receiver, where because of problems of carrier signal recovery, you may again find the a second dimension is good. Okay. So this is an example deliberately taken, where on the one hand we can see that it was not necessary to describe 2 points using 2 basis functions, but because the corresponding modulation scheme is very important, at least the phase modulation scheme BPSK, where again for receiver description, general description, it may be a good idea to talk about two orthogonal carriers. Well, I'll tell you, we have already studied about the baseband equivalent structure for the modulator. Have we? Have we not? I path, Q path, if you remember, for the modulator, in phase path, quadrature path. Okay. Because you are designing your BPSK modulation scheme, just think back about that I path, Q path description of the modulation scheme using two quadrature carriers of sine and cosine, and let me know later on whether the same structure can be followed also for BPSK modulation generation. Okay, like to counter to support his view that well, two basis functions were not necessary. Instead of choosing the point here, I could as well, yeah, if I would have chosen a point here, okay, and accepting what he said that this other point should be opposite to this, okay, and to honor his wish that okay, let this also have the same energy, so equidistant from the origin really. If I choose this, then instead of choosing S1 here and S2 here, I could equivalently choose them here, so that I could avoid talking about any phi 2 axis. I have one orthonormal basis functions, orthonormal to whom also need not be answered. Yeah, okay. So one axis, any axis you choose, okay, and consider some two equidistant points carrying equal energy. You get a binary modulation scheme. Fine. The point is that this specifically indicates that now when you add your carrier modulation, carrier part there, okay, and if the carrier phase is not always constant, then you will find that the transmitted symbol does not always lie on this axis. If your carrier phase is always constant, there is no variation because of any parameter, physical parameter, then this description is fine. This description is a bit bookish, we can say. In a practical situation, it may be of good sense to represent it in a somewhat general manner.
So even if the carrier doesn't is not in phase, like this point is like on the axis, still like some component of it will lie on the axis.
See,
that
today,
will be like enough to ensure like whether it's S1 or S2.
pardon?
So what I'm saying is like even if the point doesn't lie on the axis, it will lie somewhere in the vector space.
The other space is not defined. The signal space itself is this line, signal line.
Some projection on this axis.
There is no question of projection because when there is only one dimension for the signal space, what is that signal space? Is a line, is it not? So the moment I avoid talking about a second dimension of phi 2, my signal space reduces to a line. This is phi 1. Arbitrarily I choose this to be origin, a point with zero energy. So your signal points must always reside on this line. Maybe, yeah, in a carrier modulated form, yes. Now the point is that today if you transmit with a carrier with some phase, tomorrow if the phase changes by some degree when you switch it on, I will say just academically that okay, now because your carrier phase is somewhat different compared to yesterday's, really it is no more the same signal point that you are transmitting. It's of academic interest, I mean it does not matter practically. Yeah.
What is the variation in points and phase? This pictorial view.
See, I would like to talk about phase only after adding the carrier component. Okay, this description I would like to say that is valid for both baseband low pass equivalent signals as well as carrier modulated signal. The connotation of phase is easily understood when you talk about a carrier modulated signal, where for example, again as an example, quick example, for two dimensional signal space, the usual basis functions that can be taken are cos omega c t and sin omega c t over the time interval 0 to t. They may be basis functions, okay, fine, along with the corresponding baseband signal, okay, so that the signal energy is also maintained over there. Now, this cos of omega c t with unit energy, if that is viewed as one basis function phi 1, the other one is sine of basis function over there, then I can talk about the phase deviation. If there is a phase change for the oscillator tomorrow, then that phase change can be described that okay, there has been 30% offset. Now, a signal with a 30% offset, that means the point has shifted to this. When I have considered a second dimension, okay, I will say that the cos component is giving somewhat less today, and there has been a sine component today which was not there earlier. Okay, but anyway, this discussion is not very important for practically for BPSK. Okay. More so because in the receiver there is a carrier phase recovery circuitry if you are going for coherent demodulation. Okay. But for receiver description, because there is maybe phase offset, this description of two dimensional signal space, even though there are only 2 points, could be as well shown on the same axis, single axis, is good one. Anyway, come back to our question really. In fact, more important at the moment is to understand how we can utilize this signal space description. First thing is that if I mean suppose this S2 I have not chosen, I am not so intelligent really. So, I have chosen S1 here and I have chosen S2 here, not here. You are in a position to comment whether the choice has been good or bad, I guess. As a modulation scheme, if I say that I have come up with a new modulation scheme and these are the two signal points in the signal space, you should have some comment to make. Is it acceptable first of all as a modulation scheme? Yes, acceptable. Why not? Isn't it? Because both the signal points can be decomposed in terms of the basis functions, so they are acceptable. Yes, but it is not very good really. Or yes, it is good, or no comment can be made. Yeah, because we can see that they have got different energies. So, one question would be, why is it that you are transmitting two symbols with different energy? How does it help you in the modulation scheme? Okay, unless there is a special reason, there is no reason. I mean, you should not transmit that really. So, they should be transmitted with equal energy. Okay, but in some cases there may be a sense as well, like let me say, not as this one. I am just trying to give you a few quick examples so that you can start thinking about these issues, okay, and do some practice. Suppose instead of choosing S2 here, I have chosen S2 here. Is there anything wrong? I mean, so far as modulation scheme is concerned, no, acceptable. What is the difference? Same energy. I mean, the energy is different. So, one I am transmitting with a higher energy, the one with a lower energy. Can you quickly guess? I mean, whether you can think about actually some modulation scheme which may follow this. Yeah, PCM. Yeah, pulse coded modulation. Pardon? The spectrum. Well, you are talking about the quantization steps. Well, that's not a good example. That's not a good example because
The difference is not so appreciable there actually. So like in the levels you have.
mhm.
So in this case, sir, when you transmit of them the same phase, so you would like the difference in energy to be appreciable. So it's in case there is some distortion, you don't mix the two signals. So sir, in PCM you won't have appreciable difference in the two signals, right? Because the levels are quite close to each other. The quantizer levels are quite close to each other.
Are you talking about the quantizer output only without any coding? But PCM ultimately stands for pulse coded modulation, isn't it? You quantize the samples and then you code. After coding, what do you get? A group of bits, isn't it? And the normal practice is that for transmission, we transmit them serially, is it not? And now, of course, I am talking about that even though the bits will come serially to your baseband processor, now that we are talking about m symbols at a time, not only 2 symbols in general. So, we may again consider small group of bits, say 4 groups at a time to consider one symbol. So, that we have 16 symbols, 3 bits at a time. So, that we have got 8 symbols defined and hence 8 samples, 8 signals and 8 points in the signal space and like that. So, that PCM example does not fit in this context perhaps. Yeah, PAM, pulse amplitude modulation. Okay, pulse amplitude modulation is one example really where you are transmitting whether it is 1 or 0 or 4 values by the amplitude of the pulse, and when the amplitude is different, obviously the energy carried by them is different over there, is it not? Okay, tell me if I would have chosen S2 here at the origin, anything wrong? Not wrong. So, what I am simply saying is that one signal I transmit with good energy, the other signal I transmit with 0 energy really, I do not transmit anything. In fact, we had this example some time back in some other context, really we said that it is on off kind of modulation scheme, okay, isn't it? Yeah, right. the point is that you can think of various modulation schemes by simply considering a signal space diagram with you. You can choose various points there. Okay, if I suddenly increase the number of such signal points to say 16, 32, you will find that it needs some kind of rational thinking and placement of the points, so that at a time you can take care of many good properties of the modulation scheme. So, the modulation scheme that you want to design, say, depends on you. If you can incorporate more and more good properties there, you come up with a good modulation scheme. So, towards that, one common issue is that it is not only the issue of modulation and transmission, one has to receive the signal appropriately without confusion, and uh, the decision error somewhere before we say ultimately which bit or which groups of bit was transmitted, that decision is as correct as possible. So, most of the signal point design in the signal space is ultimately focused towards that. The associated issue here, which again I can incorporate in this diagram, is the issue of average energy per symbol. Can I talk about that also in the signal space description? The moment I choose my points in the signal space, okay, I know the energy associated with each symbol or each signal, okay, and usually, as I started in my discussion, in my assumption that all the symbols are assumed to be equally likely, we assume that, isn't it? So, I can talk about the average energy per symbol, even the probability of occurrence of each symbol, and hence the average energy, and then by considering a large period of integration, I can even talk about the average power of transmission, average transmission power, is it not? Okay. This transmission power is a very important issue. Okay. So, to design a good modulation scheme and then incorporating the corresponding very important issue of good demodulation scheme, okay, it should be good to choose signal points very intelligently, very in an ordered fashion, such that the problem of detection is well understood, is possible, feasible without much of complexity, okay, and we get the best possible result in decision making. The second issue is that we should also ensure that the average transmission power is minimized. Like, instead of choosing S1 here and S2 here, one could choose S1 here and S2 here. What is the essential difference? The second chap is unnecessarily asking for larger transmission power.
So that depends on the charge of origin.
This origin you have to start, choose at the beginning, okay, you can place anywhere, and then with reference to that the axis is placed really. Once those are placed, so now compared to the earlier situation of S1 being placed here and S2 being placed at the origin, now if I change my style and say that let S2 be here and S1 let it be here, I have drawn it further away. So, what I have essentially done is that I have increased the power associated with S1 or increased the energy fundamentally, and then considering that both of them are equally probable with probability 0.5 really, I can say the average transmission power has increased, isn't it? So, the point should be so designed that the average transmission power is not unduly increased. Okay. That means this problem, this example becomes more prominent if I consider more number of points, more than 2 really. Just to give you some flavor of another important modulation scheme, let us, if I consider there are 4 points, 4 signal points, just, and suppose we have chosen 3 of them here, and the 4th one I have chosen here. You have to answer me specifically whether this is at all a valid modulation scheme, first question. Second question is, if yes, then in terms of average transmission power, is it the best? If no, then the third one is, guess which one would be the best. The fourth point, first of all, should be equidistant, because these points are equidistant from origin. All of these symbols have got same energy. So, why not the fourth one? When all the symbols are equally likely, so this also should have equal energy. So, maybe somewhere here. So, if I draw a circle, should be on a circle somewhere, at least that much to reduce the average transmission power. So, this point could be here, could be here, could be here, but you also said that not necessarily that only, let it be here, because that also takes care of something else. Maximum separation and this separation is fundamentally necessary for the purpose of good detection, isn't it? Good decision ultimately, isn't it? So then my point is proved. This signal space diagram can be utilized for designing modulation scheme, even for picking up the modulation points or the signal vectors such that the average transmission power is rationalized, okay. And not only that, a very important issue is also to design the points, place the points such that the corresponding decision making process in the receiver is going to be the best possible. Only thing is that we have to formalize what is that best procedure, okay. Sorry. Towards that, as I said, we will it's time, is it? Yes. Oh, sorry, okay. So let's stop here today. In fact, that decision procedure has got a very famous name. It's known as maximum likelihood detection principle. So we are going to discuss about that in the next class. Thank you.